Okay, so as we go small, scaling law plays an important role to ensure the performance of the MEMS device. So it is an observation of how the device work at the different size. So how we're going to verify this? So all the device of the MEMS device, the characteristic of the length plays important role. Okay, so the performance vary on, let's say, the sensitivity, the volume, the surface area will be expressed in terms of the function of the, and then it will be simplified to check the effect of the scaling the length towards to the performance, either for the capacitance or the heat dissipation or the surface area. So as we can see here, the law of physics will make the small world look different. So previously, as we explained before in the previous video, the surface tension will be much more larger than the force, right? So, and then the surface area play important role inside the smaller device. So in order to interpret that, so we will denote everything with what the notation of the length. So let's say first the volume. The volume will be equal to L cube, and then for the surface is actually the area, that is L squared, and then for the force is L squared too. We are going to assume that the mass density of all the small device is constant. And we have the interpretation of the resistor and the capacitor here. Resistor will be inversely proportional to the length, and also the capacitor will be proportional to the length. On top of that, we also have frequency that will be inversely proportional to the length. So in a smaller device, the law of physics will be a bit different because of some of that is not important in the macro scale, is very important in the bit micro scale. Okay, so first let's see the scaling law between the surface area to the volume. So the ratio between the surface area to the volume. So first let's calculate what is the surface area for the cube shown here. So you know the surface area, we have 6 flat surface here. 6 multiplied by what is the area of one surface, that is A squared. So we got here 6A squared. How about the volume of the cube? There is A cube. Okay, so what is the ratio between the surface area to the volume? Is equal to 6A squared divided by A cube. So if we cancel down, it becomes 6 over A. So as we scale down, the volume of the volume here, because it's a cube, right, will decrease rapidly compared to the surface area. So in other words, as we scale down, this length become decrease, the surface area over volume also will increase. Why? Because the surface area will give more impact compared to the volume, because volume here is a cube, but the surface area here is 6A squared. Okay, let's see one example. So just now we can get the surface area divided by V is equal, for the cube is 6A squared divided by A cube, right? And we simplify, it becomes 6 over A. So let's give one number. See, if macro scale, so A equal 10 is what we call macro scale. It's not the MEMS device. So let's say this is a smaller device, that is micro scale. So if A equal to 10, your surface area over volume ratio will become 0.6. But when your A becomes smaller, that is A equal to 0.1, A is the length of the cube, your ratio of the surface area to the volume will become 6 divided by 0.1 is equal to 60. So what can we denote here? As the length decrease, means it become micro scale, right? Your surface area to the volume ratio will increase. So this means that your surface area will be more affected compared to the volume. Okay, so let's see the comparison when we go smaller. So let's say the length of the cube here is from 10, 1, 0.1 and 0.01. So let's calculate the surface area with ratio of the surface area to the volume. So this one is as, you know, volume is A cube, surface area is 6A cube. So when we simplify, you can get the ratio is 6 over A. So for the macro scale, so you can get here is 0.6. As we go smaller, the surface area ratio to the volume will be more higher. So as we go smaller, the surface area ratio to the volume, so this to the volume will become higher, right? So what does that mean? So if we look at the volume number here, as we go smaller, the volume will be much more smaller, right, compared to the surface area. So if we're talking about the heat dissipation, so it will directly relate to the surface area. How we're going to cool the device? So in a smaller device, so this is a smaller micro scale device, in having a large surface area here, so it easier to get cool down. So in a smaller device, as we go smaller, the heat will dissipate much more faster as we go. So as we think of the logic, smaller device will dissipate heat more faster compared to the larger device. Okay, so let's see the second scaling law of the spring constant. So what is actually spring constant? So you have a cantilever beam here. So your beam is having the length. This is the length. This is the width. This is thickness. And when you apply a force here, so this cantilever beam will start to bend. So that's why we have what we call spring constant. Okay, so this is the formula for the to calculate the spring constant. So K is the spring constant, E is the Young modulus. What is Young modulus? Young modulus is the ratio between stress over strain. W is the beam width, T is the thickness, and L is the length. So on all these parameters, which is related to the length related scaling parameters, so we denote with W, T, and L. So please take note that this Young modulus is not related to the scaling, because this is what we call Young modulus is equal stress divided by strain. So what is directly related to the scaling parameters is only W, T, and L. Okay, so let's replace all the scaling parameter. To L become L, W width, right, the width of the beam. So it become area A multiplied by L, and the thickness is B and L. Okay, so what we're going to denote here, K equal E is a Young modulus. What is W here is AL. What is T here is BL multiplied by BL cube. Okay, and then you have divide by 4. L will replace with capital L cube. So you can get here the same, right? So we're going to simplify this formula and take out the constant. So it becomes EAB over 4. So we want to see what is the L effect to the spring constant. So become L power of 4 divided by L power of 3. So it become cancel. So this is the constant. We are going to ignore the constant and L. So this is the constant. So how is the relation between the spring constant and the L? So it is actually proportional. So as we can see here, spring constant is proportional to the length. So as we go smaller, as the length decrease, your spring constant also will be decreased. So as the device goes smaller, your spring constant becomes small. So how we can relate this? So this is your fixed part, right? So as you go smaller, so this is, let's say this is a micro scale and you have a smaller cantilever beam here. This is micro scale, okay? So as the length decrease, your spring constant also will be decrease. So what does that mean? So it become more flexible to bend. So the bigger size, the macro scale of the device is difficult to become flexible. So if you go to micro scale, due to the spring constant also will be decreased, so it will become more flexible. So why we need this flexibility? Because now we are moving toward to the wearable sensor, right? Wearable sensor. We have sensor at our body, so we need the device to become as the more flexible, the better the sensor for wearable electronics.